Hi everyone, I am Abhijit Mondal from Indian Institute of Technology, Kharagpur. I am going to present my work, Federated Adaptive Bitrate Live Streaming over Locality Sensitive Playback Policy. Let's start with DAS or Dynamic Adaptive Streaming, which is the base of our work. In case of DAS, video first need to encode it into multiple quality level, and then all those quality level have to chunk in multiple segment with equal playback duration. And when a player wants to play those video, it have to download one chunk at a time and play it. While downloading those chunk, it also closely observe the network quality it is getting, and based on the network quality it decide which quality level it is going to download for the next chunk. There are two type of dash streaming. One is video on demand or static streaming. Another is live. In case of video on demand, all the videos are already available in the server, and any player can play any video and any part of the video anytime they want. However, in case of live streaming, videos are not already available. Rather, it is live stream from the former event, and as videos are not available in the server, all the players have to stick to the live version of the video only. For live streaming, their setup start with the live capture device, which capture the video and upload it to the server for preprocessing and deciphering. This entire procedure requires some time, which may be from 30 seconds to 1 minute. And once this process is done, each segment are placed into the CDN server. And then once that segments are available in the CDN, uh, players, they can download segments independently and play it. All the players download those segment independently and play independently, even if they are in the same network. We want to change it. We want them to download once and share among themselves instead of downloading independently. To do so, first we need to discover the players which are in the same LAN, not in different LAN, and then we need a scheme to share video and download video segments, so that there is no there will be no free rider, and overall QoE is improved for each and every player. For that, we will form coalition among players in the same LAN, and then share video among players within the coalition only, not with anyone else. And on top of all these things, we will form a download and sharing policy, so that no free rider can enjoy the video. So how we are going to discover or find nearby player? For that, we can always use LAN broadcast. However, LAN broadcast have the range very limited. It's limited to the broadcast domain of the network, and that is very limited. So we want to expand the range by proximity server, which can provide more more client information or more player information in the vicinity. But it is not sure whether all the players are communicatable, or even if communication is possible, is it feasible due to the distance or the network capacity problem. So we use Alto server, which provides us the network map and cost map, which we can utilize to understand the feasibility of communication between two players. Once we know how to discover it, let's look at how can we form the coalition. For that, first there is a live video streaming is going on, and one player start playing the video by downloading the segment directly from the CD, and simultaneously it start looking for other player, first with the LAN broadcast, where it might get a player, may not, and then it will look for proximity server and asks it for more player. Proximity server can give more player information, which might be in local network, might be in different network, or in a different network in the sense of it have to go through LAN. So the player cannot communicate with the players which are not in the LAN network. So it will look for the compatible players in the local network. Compatible means whether whether those players are close by or communication cost is low enough, or the screen size or the target quality is equivalent. If a player is not compatible, the, they cannot form any coalition. However, if players are compatible, they can form a coalition and play the video. Similarly, here, like red guys in the left side network and green guys in the right side network, they form coalition and play the video by sharing the chunk. Once we form the coalition, we have to understand how we are going to download the chunk and share among themselves. For that, they first decide which segment, who is going to download which segment, and once it's decided, they are going to download. They are going to decide which quality level they are going to download for that particular segment. For example, here C3 decided to download F1, and as F1 is required immediately, it is going to download lower quality of the F1 so that it can be downloaded fast. But F2 or F3 don't require immediately, so client C2 and C1 goes for the higher quality level of this segment. Once they decided the segment quality, they simply download it from CDN and then share those segments among themselves. Now, this downloading and deciding which segment they are going to download, this requires some calculation, and for that reason, we decided to go for leader-based approach. Here, leader are the downloader. So first, there will be one downloader who is going to select downloader for the next segment, that is SI, and when that next downloader understand that he is the downloader for the SI, he is going to decide the quality for the segment SI and start downloading it. After that, while while the segment is being downloaded, it also decide who is going to download the next segment, that is SI plus 1, and this cycle goes on until video ends. Now, for selection of next downloader, we use this simple formula which provides us the minimally loaded players. Here IX is the idle time. Idle means how long it haven't downloaded any segment, or DQ and DL, which are the load or pending download load for the player. So this entire formula gives us the player which is least loaded or which is idle for long time. Once we select the downloader, we go through this flowchart to find out the quality of a segment. This takes two-step approach. First step, to find out suitable bitrate the client can support based on his own history, and then based on the suitable bitrate and last bitrate, it decide which quality it's supposed to download for that segment, so that there is no fluctuation uh, in the video runtime. For that, it checks last bitrate. If last bitrate is worse than the current suitable bitrate, then it might increase the current bitrate by one level up from the last bitrate. If it is not, then it will take an average of the last bitrate and suitable bitrate and download the closest one. Now, all those things are pretty sound, but there might happen some cases where a player cannot download a segment before playback time. For in that cases, we devise a way to download those segment by other player. We call it forceful self download. Please assume there is two player 1 and player 2, and player 1 is responsible for downloading segment 1 with quality QK, and the playback time for segment SI is this blue line. In that case, we will decide a deadline for downloading, which is red line here, for SI to be downloaded, and the difference between the download deadline and the playback time is TD, which is enough time for player 2 to download the same segment with the lowest quality available. Now, If player 1 able to download the segment before the deadline, everything is well. But if it can't download it in deadline, then player 2 start downloading the segment as soon as deadline crosses. And it after that it might happen that player 1 download it before player 2, or player 2 download it before player 1, whatever. But this entire thing gives a guarantee that there will be less amount of stall due to download failures. Now, how this we have devised every fail-safe mechanism, and same time we devise the algorithm. How can we implement it? For that, we modify the existing dash architecture, which mainly have three modules. One is buffer controller, ABR controller, download manager, and here ABR controller basically handles the decide the quality for next segment. We add two more modules here. One is FLiDASH module, another is remote buffer manager. FLiDASH module intercept the communication between ABR controller and download manager and decide which segment it need to download based on the coalition decision. And accordingly, it asks download manager to download the segment. Remote buffer manager keep track of the segment available in the other players and fetch those segments when required by the buffer controller. So this is all, and we decided how we are going to use this. So let's implement it and evaluate it. For that, we use a event-driven simulator, which is extension of Pensif simulator. Pensif simulator is we use Pensif simulator and extend it to support multiple player, where multiple players can be connected via a reference network, predefined reference network. And links of this reference network can be emulated using Mahi-Mahi network trees. And with this environment, we compare our FLiDASH with existing standalone ABRs and as well as distributed streaming system using DHT. And we compare our compare FLiDASH with 58 dacified video which are emulated to treat as live streaming, and then the total length of this video is 45 hours. Then we use a Snapd database for reference network, and we use publicly available traces for emulating the link. At this level, we want to know the quality of QoE improvement by using FLiDASH. For that, we use this particular formula, which provides us the QoE, and it is a combination of three parameters. First one is sharpness or bitrate or video quality. Second one is the lack of smoothness or fluctuation in the quality. And third one is most important, is the overall stall time. Now let's see the result. First result is the two component sharpness and lack of smoothness. We plot the sharpness in left side, and we plot lack of smoothness in right side. We plot both the result as form of CDF, and we plot CDF in y-axis and parameter value in x-axis. In case of sharpness, we expect better value, and better value means the particular ABR or system performing better. So here we can see that FLiDASH actually outperforming each and every existing system. Doesn't matter if it's DHT or standalone ABR. However, the lack of smoothness is just better. It is FLiDASH is performing better than DHT. Here expected result, or if a result are lower, then that is better. So only DHT performing very bad, but FLiDASH is equivalent or just little worse than the existing one. The reason behind this one is that FLiDASH by default play video in very high quality, and in those high quality level difference between two level is very high. So one single fluctuation can cause a very high bitrate variation. And next we will check out the uh, important parameter, that is timeout or stall or rebuffering, and the overall experience. In left side we plot the rebuffering, and on right side we plot the experience, and in both the cases we plot the CDF only, where y-axis represent the CDF and x-axis represent the parameter value. In case of rebuffering, we want less rebuffering, so lower value is better. Now the rebuffering achieved by the FLiDASH is equivalent or comparable to all the standalone ABR system. However, DHT performing bad here. And for uh, for the same reason, using not only for rebuffering and the uh, average bitrate and bitrate variation, we can see that uh, QE is far better for FLiDASH. It's outperform each and every system available, and DHT perform very bad. Rest of the rest of the ABR or standalone ABR performing almost equivalent. Now, at this point, we understand the QE thing. Whether we are gaining anything in terms of the CDN load. For that, we measure the CDN load in terms of data transfer and in terms of number of requests performed by the players. And we can see that downloaded data amount is uh, less than everyone, but it's slightly equivalent to the BOLA, but its DHT is far less. However, the number of requests for FLiDASH is way low, and for each and every other AVR, the number of requests is exactly same. Here the thing is, although DHT download very less amount of data, it's also provide very less amount of bitrate or average quality. However, in case of FLiDASH, this is not the case. FLiDASH provide very high quality video, and though it download pretty low compared to any other standalone system. Now next experiment we done to understand whether each and every player gaining by using FLiDASH or not. For that we use this formula which returns positive if the parameter is performing better for FLiDASH than the other system, and if it return negative value if parameter performing worse than the other one. And we plot the result using box plot for sharpness and experience only. And we find that in terms of sharpness, if we compare with any other existing ABRs or in any other system, FLiDASH is far better. That it means that every player gaining something in terms of sharpness when it is using FLiDASH instead of any other existing system. That thing is also true for the this this statement is also true for QE benefit. However, for BOLA, in 40% of the cases, users are not gaining by using FLiDASH. Rather, it is losing something. But this is not the case for everyone else. However, BOLA provide very low video quality, so that's the reason video BOLA actually provide better QE, as it does not fluctuate or does not stall. After this, we wanted to know the effect of coalition size. Till now, all the experiment we have performed, we use the coalition size of 4. Now we change it from 3 to 10, and then we measure the QE, data transfer, and fairness. Here the plots in very left side, I plot the overall QE by per each player, and then we plot the average data transfer, that data transfer per player, and then we measure a fairness index, joint fairness index in terms of QE. In terms of overall QE, we can see that QE is actually increasing when we are increasing the coalition size or group size. And uh, similarly, uh, the download and upload also, the upload actually increasing when we increase the coalition size or group size, but same time the download amount is decreasing. And joint fairness index actually is almost 1 for each and every group size or coalition size. However, the interesting thing is when we are going to increase the coalition size, the amount of data each player have to upload is huge, and that will create overhead for the player. So that is not desirable. We choose 4 because 4 is giving better QoE than 3 or any other, and it's also create the overall load for the CPU. It reduce the load for the CPU. So this is the result of coalition size. Now we want to the uh, check the effect of communication delay threshold, that which threshold were considered for safe to communicate during formation of coalition. And by default we take around 4 milliseconds, but in this experiment we change it from 4 milliseconds to 256 milliseconds and measure the average bitrate and QoE. We see that there doesn't have much difference or any significant difference when we change this uh, threshold. However, uh, we we empirically saw that the load in the network increases when we change the when we increase the threshold, uh, as large delay means the packet have to traverse large number of router and switches. And this is there are a lot of other experiments we have performed which are available in the paper. In conclusion, I like to say that we have developed a middle box free collaborative adaptive live streaming system which have very low overhead and which does not use any internet traffic. Rather, it uses the local network, which is most of the time underutilized. In uh, At the end, I like to thank Dr. Gao for shepherding our paper, and I like to thank all the reviewer for reviewing our paper, and thank you all for attending this session. Thank you.